Today, finite fields made easy. I've picked these problems here because I think it's important to have a crystal clear understanding of finite fields if you're going to eventually do harder problems. If what you can see on the screen is easy and you immediately know the answers, well then this is not the video for you. You should stop and move on. So let's go to the first question. How do we construct a finite field of 6 elements? And the answer is we can't. For a finite field, the number of elements must be a prime, for example 2 or 3 or 23, or it must be a prime power, for example 8, which is equal to 2 cubed, or 25, which is equal to 5 squared, or 125, which is 5 cubed. So all we have to write here is that no such finite field exists, and we can move on to question 2. Now, where you're constructing a finite field with a prime number of elements, the way to do that is to create a set starting with 0, then 1, 2, all the way up to 1 less than the prime. So in this case we'll go up to 6. Now one of the things you need for a finite field is closure under both operations, which are normally addition and multiplication of some sort. Now in this case, if we add or multiply 2 elements, we may well get an answer that is not an element of this set. For example 6 and 5. And so all we need to do is modify the operation. So we'll make it addition modulo 7 and multiplication modulo 7. And then we've done what we need to do here. It also gives us a quick insight into why you can't have 6 elements. One reason is that if you try to do this with 6 elements, then some of the elements, for example 2, doesn't have an inverse under multiplication, as you can see here. So to question 3. Firstly, don't try to use the numbers 0 through to 8, because you'll have the same problem that we just saw. The numbers 3 and 6 won't have inverses. So here's a critical idea. What we need to do is move away from using sets of numbers. So there are 2 ways that I'm going to show you. The first is that we can use sets of polynomials. So how could we construct 9 polynomials to make up this finite field? Well, here's one way. We can use the fact that 9 equals 3 squared, so we have sort of 3 constants and 3 coefficients in front of the x term, and we end up with these 9 polynomials. Now, the first thing that we can focus on is addition. This is a field, so it has to be closed under addition. So one of the problems is if we add, say, 2x plus 2 to x plus 2, well, we get 3x plus 4, and 3x plus 4 is not one of the polynomials I've got up there, so I've got a big problem here. It's not a field as far as we've gone so far. So one way to solve this problem is that we'll say that we'll work modulo 3 for the coefficients. So the 3 in 3x, well the 3 will just become 0, the 4 will become 1, and we're just left with number 1. And 1 is one of the polynomials that we've got in our 9, so we've got some closure there. Just for another example, x plus 1 plus x plus 2, so we add those 2 elements, x plus 1 and x plus 2, we get 2x plus 3, which becomes 2x. So what we can say is that we're adding, and we'll also multiply in z3x. We use this term here. So the x indicates that we're talking polynomials, and the z3 means that the coefficients operate addition and multiplication modulo 3. So that's pretty good so far. Now we've got another problem. What happens when we multiply 2 elements? Let's say we multiply 2x plus 1 times x plus 1. Well, now we get 2x squared plus 1 in this z3x world. And the problem is 2x squared plus 1 is not one of these 9 elements. So once again, we're breaching the closure conditions. So as it stands, this isn't a field. So we've got to solve that somehow. And the way to do that is that we'll take the remainder when we divide by a polynomial of degree 2. So something like x squared plus 2, 2x squared plus 1. Now we'll see in a sec that we need to have an inverse. Each element has to have an inverse. So we can't just use any polynomial to work out these remainders. We have to pick an irreducible polynomial. That is a polynomial of degree 2, and it must be irreducible in Z3x. So this goes beyond a little bit the thrust of this video. So I'll just quickly put up a proof here that x squared plus 1 is in fact irreducible in Z3x and move on. So we use that modulo for both addition and multiplication, and that ensures that, one, we get closure under multiplication. Because we're taking modulo x squared plus 1, everything will end up, when we multiply, will end up being one of these 9 elements in our set. And secondly, every element has an inverse. So for example, if you try out, let's see, what did I do? X. What's the inverse of x? Well, x times 2x equals 2x squared, which is equal to 2 times x squared plus 1 plus 1. So when we look at the remainder of that, modulo x squared plus 1, we see that we just end up with 1. So x times 2x equals 1. So the inverse of x is 2x. So x does have an inverse. Okay, so now let's just put up the answer. You might want to show off the fact that you know a nice compact way of expressing this as z3x modulo x squared plus 1, but I'll also put all the details there that you would probably want to put in a answer to the question. There is another way of describing a field with 9 elements that doesn't involve polynomials in the normal sense of the word. So let's have a look at this. So a suitable field is Z3 alpha. So we've replaced x with alpha now. So what's alpha? Alpha is a root of the polynomial x squared plus 1 in Z3x. And we now form the elements of the field, the 9 elements, sort of in a way as we did before, but rather than using x, we're going to use alpha. And I hope you can see that if we add 2 of these elements together, and if we add the coefficients modulo 3, then we'll ensure that any result is one of the elements of the field. So we're not going to breach the closure rules when we add. Now, what do we do when we multiply? Well, we can simplify, if necessary, by recognizing that alpha squared plus 1 is equal to 0, because that's what it means for alpha to be a root of the polynomial x squared plus 1. So let's have an example. If we multiplied 2 alpha plus 1 times 2 alpha plus 2, we get 4 alpha squared plus 6 alpha plus 2. Now we can simplify the coefficients because we're in mod 3, and we end up with alpha squared plus 2. And now we need the next step, and so we recognize that it equals alpha squared plus 1 plus 1, and of course alpha squared plus 1 is equal to 0, and so we're just left with 1. So this little trick here ensures that when we multiply any 2 elements, we make sure that the result is one of the elements of the field. So that's it for finite fields. I hope you found it useful.